Welcome to Maths with EJD. In this video, we still continue with hyperbolic functions, and we get to talk about evaluation of hyperbolic functions. Of course, this is a very straightforward one. Let's go. So, hyperbolic functions, much like trigonometric functions. You see, we keep comparing hyperbolic functions and trigonometric functions. Much like trigonometric functions are used to describe, they are used to describe a variety of phenomena, phenomena, particularly in areas like calculus, physics, and engineering, Okay. So again, just as a quick rundown, the basic, okay, I guess I want to change at this point. The basic hyperbolic, let me write that properly. The basic hyperbolic functions are defined as, first of all, you remember sinh x is equal to e raised to power x minus e raised to power minus x divided by 2. Then you have cosh x, which is e raised to power x plus e raised to power minus x divided by 2. And of course, you have tanh x, which is sin x over cosh x. And that simply means you have e raised to power x minus e raised to power minus x divided by e raised to power x plus e raised to power minus x. Okay. So then we can now talk about their reciprocals. The reciprocal of sin x, that's 1 over sin x, is actually the same thing as cosh x. That is cosh x. So it is 1 over sin x, and that means it is 2 over e raised to power x minus e raised to power minus x, easy. And then you have the reciprocal of cosh x, which is 1 over cosh x, right? And that is sesh x. In the previous videos, we've seen their graphs. We saw their graphs like that. So cosh sesh x is actually the reciprocal of this, which is 2 over e raised to power x plus e raised to power minus x. And then lastly, we have the reciprocal of, this looks a bit strange. Let me do it properly. Minus x, right? So then we have the reciprocal of tanh x, which is cosh x. And that is simply, just invert it. You have e raised to power x plus e raised to power minus x all over e raised to power x minus e raised to power minus x. So these are the basic hyperbolic functions we know. So let's do some evaluations, since our focus today is to evaluate some of these functions to see what they look like. Okay, so let's do some example calculations. Or let me just say evaluations, right? Example evaluations. Just straightforward. It's all about inserting the values that you're interested in. So let's say for number 1, we want to evaluate sin 1. So that means wherever you see x, you put 1. So already you know sin x is e raised to power x, So anywhere you see you should have x, you put 1. So that's e raised to power 1 minus e raised to power minus 1 all over 2. and that is approximately, e raised to power 1 is approximately 2.7183, the exponential form, and then e raised to power minus 1 is 0.3679, all of that divided by 2. And of course, that is approximately 2.3504 divided by 2, and that ends up being 1.1752. Okay, so interestingly, you can actually try it out on, you can check that on Desmos. Desmos is a go-to place if you want to plot graphs and do all that. So now Desmos, just go to desmos.com, and then you can do it brings this straight. So just say sinh1, right? Sinh1, and it gives you the answer 1.1752. 1.1752, and that is exactly what we got here. 1.1752. That's the result. Okay, so that is sinh1. What if we want to do cosh1? What does cosh1 look like? 2 cosh1. That means, cosh is e raised to power x, that's e raised to power 1, plus e raised to power minus 1 divided by 2. And that is approximately 2.7183 minus 0.3679 divided by, it's plus now, divided by 2. So that's approximately 3.0862 divided by 2. And the final result is approximately 1.5431. 1.5431. And if you take that back to Desmos, cosh1. So cosh1. So that's 1.5431 to 4 decimal places. So that goes easily. Then let's talk about tanh1, for instance. Tanh1. So we're just going around evaluating. So if you want to evaluate tanh1, so anything you're evaluating, just put that value for x. So you have tanh1 is e raised to power x plus e raised to power minus x divided by e raised to power x plus e raised to power minus x, which is simply, interestingly, we can just say it is sinh1 all over cosh1. That's also another way to look at it, since we've evaluated this already. So sinh1 is, that's approximately, sinh1 that we got before was 1.1752. So that is 1.1752 divided by 1.5431. 1.5431. So that's approximately 0.7616. So we can verify again from Desmos. So if you go back to Desmos and do tanh1, so that is 0.7616, like we have it right there. So we move on to evaluate some other ones. So let's try sinh0 and cosh0. So let me say number 5 is, okay, I want to change the mark color. So 5, we have sinh0. Of course, sinh0 is e raised to power 0 minus e raised to power minus 0 divided by 2. That is 1. E raised to power minus 0 is like 1 over, okay, well, let me do the whole thing. So you have e raised to power 0 minus 1 over e raised to power 0 divided by 2. E raised to power 0 is 1 minus e raised to power 0 is also 1. So 1 over 1 divided by 2. That's more like saying 1 minus 1 over 2, which is actually 0 over 2. And the answer is simply 0. So sinh0 is 1. So that is like the first part of that. So what if we have to talk about cosh0? Cosh0. Cosh0 would be e raised to power 0 plus e raised to power minus 0 all over 2. Of course, e raised to power 0 is 1. Plus, Okay, well, let me do this same long thing I did before for clear understanding. E raised power 0 plus e raised power minus 0 is the same thing as 1 over e raised power 0, and that's all over 2. So we have e raised power 0 plus, now e raised power 0 is 1 plus 1 over 1 all over 2. So that's like 1 plus 1 divided by 2. So, and there's some measure of exactness here. So 2 divided by 2, and that is 1. So that means that just like cos 0 is 1, cosh 0 is also 1. Cosh 0 is also 1. That's number 5. Let's do number 6 now. For number 6, we want to evaluate. Oh, was that 5? Let's see. This is, oh, okay. I jumped something. This is actually 3. This is number 3. Then this is 4. This is 4 now. And then we have 5. We have number 5 here. This is number 5. Okay. So for number 5, we want to evaluate tanh 0. Of course, we know that is sinh 0 all over cosh 0. So sinh 0 is 0, cosh 0 is 1. So it means tanh 0 is also 1, just like tan 0 is 1. So you can evaluate stuff like this. Okay, so the next thing I like us to talk about will be approximations and series expansions. Approximations and series expansions. So approximations and series expansions. So we have similar things for trig functions, approximation and series expansions. So for the first one, okay, I'm going to make videos on power series pretty soon, so there'll be clarity on some of these things at that point. So hyperbolic functions can be approximated, approximated using their Taylor series, expansions, Taylor series expansions around x equals 0. Of course, Taylor series around x equals 0 is known as Maclaurin series, as we're going to find out later. So for small values of x, this series are particularly useful. So for instance, if you have number 1, you have sinh x, the power series for sinh x. Of course, being an odd function, right? So the same thing holds, just like in the case of sine, So you have x plus x cubed over 3 factorial plus x raised to power 5 over 5 factorial plus all that, down the line. So it's an infinite series. Okay. Then you can talk about cosh x, which is also an even function. So it is going to be a combination of even stuff like that. So you have 1 plus x raised by 2 over 2 factorial. Exactly the same for, okay, maybe not exactly the same. For sine, right? For sine, it's plus minus plus minus. But for sine, it's all plus. It's plus all the way. So for cosh, I think it's plus minus plus minus. But here, it's plus all the way. So that's how it works. So you have x raised by 4 over 4 factorial, and that goes on like that. So just the sign thing is what makes the difference. And then we have tanh x. So tanh x is such that we have x minus x cubed over 3. So it's really a special one. 2x raised to power 5 all over 15 and that goes on like that. So if you take some examples using series expansion, see what we get. So if you want to use series expansion, okay. So examples using series expansion. So we know we are talking about evaluation. So if you want to use series expansion, you can actually do the same. Say you want science. You know, we've said it already that this series are very good for, they are very good for small values of x. So let's assume that for small x, say x is equal to 0.1. You know, we can get the following. We can get sin 0.1 to be approximately, don't forget the series for sin. It's x plus x cubed over 3, this plus x raised to 5 over 5 factorial. So it means we can actually probably take the first two terms, you know, and then that is, so for x now we have 0.1. Then for x cubed over 3, we have 0.1 cube divided by 6. You know, that's 6 is 2 factorial. You know, 3 factorial is 6 rather. 3 factorial is 3 times. So 3 factorial simply means 3 times 2 times 1, and that is 6. Okay. So we have 0.1 raised by 3 over 6, and that is approximately 0.1 plus 0.1 raised by 3 divided by 6. If you punch your calculator for that, you get 0.000167. And the result is approximately 0.100167. That's what you end up getting. Okay, we want to check decimals to see what that looks like. Looks like sin 0.1. Sin 0.1. So you have sin 0.1. So that's 0.100167, like that. Okay. So that's 0.1. So you can see this is a very, it's a very nice approximation, so to speak. So, and but by the time the values become big, it may not be this reliable anymore. But I mean, for small values, that has been clearly stated already that it's good for small values. So what if we want to talk about cosh 0.1? Don't forget the expression for cosh is 1 plus x squared over 2 factorial. So what if we take just the first two terms? So for the first two terms, we have 1. You know, that one is a constant, 1 plus x squared over 2 factorial. So that is 0.1 squared. 2 factorial is 2 times 1, which is 2. And that is approximately 1 plus 0.1 squared. That's 0.001 divided by 2. You get 0.005. And that's finally 1.005 for cosh 0.1. So let's see what cosh 0.1 looks like. Cosh 0.1 in decimals, cosh 0.1. So that's 1.005 and all that. So looking very good for small numbers. Okay, then let's do tanh 0.1. Tanh 0.1. If you have tanh 0.1, the expression for tanh is x minus x cubed over 3. Oh, yeah, it's just 3, right? Not factorial, just 3. So we can take those to x minus x cubed over 3, for instance. So that's x 0.1 minus x cubed, that's 0.1 cubed all over 3. So that's the approximate value. So we always use approximate here because it's a series that has no end. So if you're whatever times you take in that series, it doesn't still give the accurate thing that you should get, really. Okay. So the most accurate thing would have been to substitute directly into the expression for each of these, all those e raised power x minus e raised power minus x over 2 kind of thing. That's where you can be sure it's accurate. So here we are just approximating because anything series is an approximation. So you have 0.1 minus 0.1 raised to power 3, that's 0.0001 or something like that, divided by 3, you get 0.000333. And the final result is something like 0.099667 for tanh 0.1. Let's check decimals again to see how that pans out. That's tanh 0.1. Yeah, that's correct. That's that aligns with what we've been doing. So that's evaluating using series. So I mean, we have used all kinds of, so far we've done our evaluation using series, and we keep referring to decimals to verify what we have done. So can we see some possible things that we can use as far as evaluation of hyperbolic functions is concerned, or evaluation of anything for that matter is concerned? So this is like an introduction to some of these very useful tools. So using calculators, using calculators and software tools for evaluation. So Desmos is a software tool which I've been introducing you to all this while. So it's a very nice one. Okay. All right. So here I'm just going to list the possible tools you can find. So for more precise or complex calculations using a scientific calculator or software tools like Wolfram Alpha, MATLAB, or Python so if you want to do more complicated stuff, right, you can use all these things. So the first one will be you can use a scientific calculator. You can use scientific calculator. All right. So you can use a scientific calculator because that's mobile and you can probably use that in an exam. So most scientific calculators have dedicated buttons for sinh, cosh, and tanh. So just make sure you're not pressing sin. Make sure it is sinh, cosh, and tanh you're pressing. So you simply impute the value and press the corresponding hyperbolic function button. So if you're looking for sinh one, so you press 1 and you press sinh. Or if your calculator is more advanced, you can press sinh and put 1 in brackets. So just master your calculator and use that correctly. Of course, you can also use Python. Interestingly, I have a playlist on scientific computing with Python, so you can use Python. In fact, I've treated the whole of NumPy array under the scientific computing with Python. So you want to check out that library, that playlist, and expose yourself to scientific computing with Python. So using the NumPy library, you can compute whatever you want to compute, you can compute it. In fact, I want to take you through that. So in that way, I'll start Jupyter Notebook. That's the environment where I run Python. Okay. And of course, that opens a kind of web page, so to speak. So that comes up pretty soon. So it shows this terminal thing, and then it opens a web page. Okay, I think it has opened already. Yeah, this is it. So I go to the desktop where I have my folder for what I'm doing currently. That is, I go to, is this desktop yet? Yeah, this is desktop. So I go to Math with EJD and I go into what now? Yeah, hyperbolic functions. And here I just open a new notebook, a new Jupyter notebook. That's what so here now. So if you want to write a code for this, I already have a code here. So just you want to evaluate all these things. So probably want to evaluate sinh 1, cosh 1, tanh 1. So you see, NumPy is actually a library that enables you to do something like this in Python. So you have to use it well. So, and the advantage of this one is that, okay, if I put the line numbers for this code now. So line 1 is where we import the NumPy library. That NumPy means numerical Python. Okay. And then if you want to evaluate sinh, cosh, and tanh of 1, you can just say x is equal to 1. And sin x is, so NP, you can only call sinh and cosh and tanh from NP. So like this, then so the last 3 lines are printing the values out. So now I'm doing, so all the values so you can see all these ones also tally with what we've done before. Sinh 1 is 1.1752. Cosh 1 is 1.5430. Tanh 1 is 0.615, blah, blah, blah. So the advantage of this is that you can just, you can keep changing the values of x. So, the other time we also did 0.1. So I can just change the x to 0.1 and run it. So it gives us all these values we also saw before. So you can keep it going like that. So here the advantage is that you just change the value of x just in one line, and then you have it applied everywhere else. So you see all of that. So so you can actually use Python also. You can use Python for evaluation, and that's really sweet. It gives you some freedom, I believe. So it gives you some freedom. So you can use the NumPy library in Python. Then you can use Wolfram Alpha. I found Wolfram Alpha as a very useful tool to, for the past 2 or 3 years, I think, using Wolfram Alpha. Wolfram Alpha is like Google for scientific computation, so to speak, and it's free. I mean, you can there's a premium version, right? But you can use the free version for so many things. So it's just wolframalpha.com. So it's this computational intelligence. It gives you that computational intelligence. So here now, if I need science something, I just say science one. Okay. And I just press enter. So it thinks about it, it processes it, and gives me, now you can even see the precision. It gives us up to, like 32 or so, many digits, in fact. So if you are interested in accuracy to so many degrees, you can see this can be less than 32 decimal places. So that's one very huge advantage of Wolfram Alpha. So you can use it for, maybe you want to do quick data fitting, quick computation, and things like that. Wolfram Alpha is really very good for this. Imagine we want to do times 0.1 times 0.1 like we did before. So in fact, without even pressing enter, it has given us the result right here. So it's more like Google for scientific computation, if you like. So, Wolfram Alpha is that excellent. So excellent. Okay. So those are things you can use. All right. Well, it'll be wrong if I don't mention Desmos. That's what we used first of all. So Desmos. So it's very good if you want to visualize graphs, you want to perform quick calculations. Desmos is actually very good. I mean, I've demonstrated how it is used. This is, Desmos is a graphing calculator. So you also remember I showed you all the graphs like sin x the other time, what the graph looks like. Then I showed you everything like cosh. You want to see all this cosh x, you can see that's the one in green. So the color beside corresponds with whatever you're looking for. Then you have tanh x. So see tanh x right there. So I mean, it's coming together like a work of art, right? Then the reciprocal of sinh is cosh x. Now, cosh x is that black thing. So you can see it's coming out beautifully, like a very nice work of art. Then the reciprocal of cosh is sesh x. Sesh x. So sesh x is that red thing that is coming together now. And then finally, you have the reciprocal of tanh, which is cosh x. Okay, that's the blue one. So you can see everything together looks like a very beautiful work of art. So maybe you can make a logo out of this. In fact, there are some logos that are made out of mathematical expressions like parametric equation and things like that. So look at the beautiful work of art that the interaction of all the curves is giving us, right? So Desmos is so powerful in helping us see all this. And so you want to use this very often. So in summary, right, we have seen in summary, we have seen exact calculation for simple values. You can use the definitions. Okay, I think I just want to write that. Okay. So we are summarizing all we have done today so far. So we have done exact calculations by substituting directly, exact calculations by substituting the value of x into the expression for each of our hyperbolic functions. So you can do exact calculation like that, right? And then we have also seen the place of series expansion. So you can use the series expansion for each of the hyperbolic functions to do your evaluations. So they are useful for small values of x and understanding the behavior near x equals 0. Then we can have tools that I've just mentioned already. So you can use, so to evaluate hyperbolic functions, you can do exact calculations, series expansions, and you can use tools like Desmos, Wolfram Alpha, NumPy library in Python, And of course, you can use your scientific calculator, right? So that's really good. So for more complex or high precision calculation, I mean, you can see high precision in Wolfram Alpha, giving us up to 32 decimal places, which is really cool. So you can use all these resources. So with this, we have come to the end of this video on evaluation of hyperbolic functions. So if you have not subscribed, you'll be missing a lot. So subscribe, hit the notification bell so you can always get alerted when a new video is released. Then, of course, comment. In fact, this series on hyperbolic functions is actually a comment from one of my friends who wanted me to make videos on hyperbolic functions. So you may also make such requests. Then I'll find time to do that. So comment, like, and very importantly, share. Let more people, come and be part of this channel so they can enjoy the great content we have going on here. Thank you for stopping by. See you later. Bye.